Okay, it's time to finally start looking at the chemistry side of physical science, and we're going to start with matter. So with matter, we need to understand both the materials around us in matter and the subatomic level. So what is matter? It's very simple. It's anything that has mass and it takes up space. So basically everything around you, even the air molecules, are taking up the space and they have a mass to them. And so all of this is matter. The only thing that wouldn't have matter is if you went to outer space, that void of outer space. There's simply nothing there, not even gases or air or anything. So there's no matter there because there's no mass and it doesn't take up any space. So when we talk about matter, since it's such a broad subject, we're going to have to start breaking it down into smaller categories so that we can label things. And essentially, the first real category you have, other than stages, because stages of matter, it still stays the same thing, but we have mixtures and we have pure substances. So let's take a look at those. So when we talk about a pure substance, we're basically talking about something that can't really be reduced to a smaller form or a simpler form. So a pure substance, you tend to be classified in two different categories: base elements and compounds. So an element is what you find on the periodic table. It's all the same atom. Now you can have large chunks of it. I would love to have a large chunk of gold, but it's only one atom that makes up that gold, okay? And so it would be a pure substance. In fact, that's one of the things that our gold coins and stuff are so valuable, if we get them, is because they're made of a pure gold, or as pure gold as we can get. So it's only that gold element in it. Now, compounds are also considered a pure substance. Even though they are two different elements combined, they're linked. They're combined through a chemical reaction. And so they're in a fixed ratio. And so like salt is drastically different from sodium and chlorine. Sodium on its own explodes in the air if it was a pure substance of a pure atom of sodium. And chlorine binds with itself and makes a toxic gas that would choke you out and looks a little green looking. And so sodium chloride, though, just makes that nice table salt that makes food, taste salty and good. So we consider this, the compound of sodium chloride, its own pure substance. Now, with mixtures, it's basically just two or more substances that are not chemically combined, and so you can still really separate them. You can get them out of each other. And there's two types: homogeneous mixtures and heterogeneous mixtures. You hopefully have heard those prefixes before, and you know this just means one, or the same. This means different. Now, with homogeneous mixtures, think about things like soda and Kool-Aid. So they're mixtures that look completely the same throughout. Like, you don't think of it being a mixture because you think, oh, that looks like Kool-Aid. You think it's just one substance, but it's made of multiple things. And in fact, it's something called a solution. And we need to take a closer look at solution. So in a solution, you have two distinct parts that come together to make the solution. So you have the solute and the solvent. The solute is like the powder of the Kool-Aid. It's the thing that gets mixed into the solvent to dissolve, okay? And so it usually starts as a solid of some sort. So you mix your Kool-Aid, the solute, into your water, the solvent. Solvent is just what is used to dissolve the solute. And so a lot of times water is used. Alcohol is also used on certain substances, but that's usually more chemical substances. So when you put the solute and you dissolve it in the solvent, you then create a solution, which is a homogeneous mixture because it looks the same throughout, but all the compounds are there. You don't have an actual combining of the little sugar particles with the water particles. The water is still there. In fact, if you heat this, you'll evaporate the water out of it and you'll end up with a powdery substance that looks a lot like that Kool-Aid. Sometimes it might burn a little if you're not careful, but if you do it just right, you can just get rid of the water and evaporate it down to nothing. If you've ever taken like salt water and made a saltwater crystal, that's the same basic premise. You can get it back out of it. So it is a mixture, but because it looks the same throughout, it is a solution, a homogeneous mixture. Now, heterogeneous mixtures, they don't look the same throughout. you can usually see the different parts for them. They're not very uniform. And so since I used Kool-Aid before, I like to think of another snack. If you've ever put M&Ms with popcorn, makes a nice little salty sweet treat. But you can see the pieces of popcorn and the pieces of M&Ms. Or like think trail mix. That's a heterogeneous mixture. So you can see all the parts and you could pick them out with your hands. But there's other types as well. That's why I like to refer to this one as colloids. So a colloid just uses the particles like we talked about with the popcorn and the M&Ms, but they're really, 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 really tiny. In fact, it has to be between 1 and 1,000 nanometers. Nanometers is very, 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 very small. Okay? And since it's so small, it ends up being suspended throughout a mixture. Fog is a very good indication of this because it's water particles that are so tiny that they're suspended throughout the air. And so that makes a colloid. You can also see this if you've ever made some just like cloudy water with a little cornstarch in water, just a tiny little bit. It has very tiny particles and they spread out. They don't mix into it, but they don't dissolve into it, but they do mix into it and they're suspended. Now they use something called the Tyndall effect, where if you shine a light in it, the light doesn't go through and it doesn't bounce off. Instead, it hits every tiny little particle and so it spreads out. This is really cool to do at home. If you won't, put a little bit of cornstarch in water, shake it up so it's nice and cloudy, and then shine your brightest flashlight through it. You'll find out that you make a cool lantern because it illuminates all around where it's bouncing off all of those things. That's the Tyndall effect. The other thing is a suspension. So think about suspension as a good salad dressing. If you mix an oil and vinegar and a balsamic vinegar and a nice extra virgin olive oil together, those particles, they stay kind of separate, right? In fact, the oil will sit on top of the vinegar because it's more dense. And if you shake it, you can get some of them to look like they kind of mix together, but they'll settle out. It's a suspension. It's suspended in those things. So now that we can classify things in our different areas of matter, we need to look at some of their physical and chemical properties. You should have learned a lot of this a long time ago, so I'm not going to spend much time on it. Physical properties, it's usually the things you can do with your senses a lot of times. So you can see the color, you can see the shape, smell the odor. If you pick it up, you can feel the mass and the volume of it. Magnetism, you probably need a magnet in order to figure out. And electricity, you might need a little of that, but you can usually figure those out. Strength, can you bend it? Does it flex? Things like that. Those are all physical properties. Think about your physical senses, physical properties, right? Chemical properties, on the other hand, it's its potential to undergo some sort of change. And so like something that's burning or rusting, cooking, or even the process that we do for creating films. Not yours now where you just take a digital picture, but back in the day when you actually had film in your cameras, you had to soak it in these different chemicals, and the chemicals bound with it and made the picture come out, really is what happens. It bound with the light energy that was in it, but it's okay. Now, when we're talking about physical properties, you also need to understand that there's two terms called intensive and extensive. Now, intensive means the properties that do not depend on the amount of matter present. So I like to think about it is if you take a piece of toilet paper, that toilet paper is white, right? Hopefully you haven't used it yet, and most toilet paper anyway is white, all right? So if it's white, then that's an intensive property. It does not matter if you have a little piece of toilet paper or the whole roll of toilet paper. It's still going to look that way, right? And things like color, odor, luster, malleability, ductility, conductivity, hardness, melting, all of those have to do with its intensive property. So even if you have a tiny piece or a giant piece, it'll be the same for intensive properties. Extensive properties, they do depend on how much you have it. So now if I was going to weigh that same piece of toilet paper, it would weigh different depending on how much of it I was using, right? So intensive is just the color of the toilet paper. It's always going to be white, it itself. And extensive, think about like the weight or its mass, its volume, its length. All those change depending on how much of it you have. One of those Intensive properties, meaning it doesn't matter how much you have, and that's really good for identifying materials, is their density. It turns out that the molecules of different pieces of matter like to hold the same distance apart, but have the same amount of mass throughout, and so it creates density. And that's really what our formula for density is it's mass divided by volume. So it doesn't matter if you have a little or a lot, because this is a ratio of the amount of matter in the amount of space that it has. That's its density. And it's good to learn this formula. Mass divided by volume will give you the density of a substance, and it's good for identifying a lot of things. Now, with chemical properties, they're much harder to put your finger on. Basically, it's after it undergoes a chemical change, because of its chemical property, it changes into another substance and it has a new identity. For instance, really oxidation is where oxygen mixes with the metal, okay? And that causes it to rust. You then have rust instead of that metal. Now, you would have a particular type of rust, but it's still something completely different. Think about your battery and when it corrodes over. You're not going to get your battery back out. You know it's time to throw it away because it's changed from the battery acid into a corrosion. Or if you burn a sheet of paper, you're not going to get that piece of paper out. You can get, ash, but that's pretty much it. But this is the big thing you need to remember with it. It includes a change in the identity of the substance. And the last portion of this is a very simple statement. It's the law of conservation of mass. Basically, whatever mass you start with, you have to end with. Now, that might not seem very important now, but later we're going to be balancing chemical equations. We're going to be putting together molecules, and the premise is whatever we start with, the atoms we start with, are the atoms we have to get out of it.